Last week we made two important handouts available to you. Have you got them both? Writing PSIs? Information sheet? You don't have, come get right now. Get the ones you don't have. What do we run out of? As I said last week, the PSI sheet condenses, I hope effectively, all the information you need to know about writing PSIs for solutions of Bronsted-Lowry acids and bases, given that we are presently in Chapter 18. You will find this handout useful very regularly. So have it with you at all times. Information sheet. You'll find the information on this handout useful throughout the term. Have it with you at all times. I repeat, this is the same information sheet, a copy of which you will receive for each quiz and exam. Because I don't expect you to memorize this stuff, but I do expect you to be familiar with it and be able to use it. This is also downloadable from the Sakai website, but you've here been given the convenience of picking it up because I think some of you may have little difficulty downloading legal size paper. I don't know, but you got it, so what? Next week, Tuesday, a week from yesterday, in-class quiz 1. If you've looked at past quizzes, you've recognized the quizzes are of composite format. Some multiple choice questions, because unfortunately during the term exams are multiple choice in nature, unless you opt for an alternative, which I'll offer to you later on regarding exam 1. And real questions. Questions where in order to get credit you have to write down your response and provide information to indicate that you understand what's going on. Believe me, that's a far more effective method to achieve education. It gives me the opportunity to see what you don't understand or do understand. But when you bubble in circles on answer sheets, I don't know anything. You get it right, you get it wrong, I still don't know anything. I'm not a crystal ball gazer. Significant deficit, drawback to the multiple choice format exam. But more on that when we get in the vicinity of exam 1. The quizzes are designed so that you can have the entire discussion class period to work on it. So don't be late, and certainly don't miss. If as yet you haven't done so, take a look at past quizzes that I've given for this class. Likely you've all done that already, I don't know. Now then, there's a bunch of gas jets back here. Nitrogen, methane, what have you. I commonly catch my microphone wires on these gas jets. I've ripped up many pants on these gas jets. They're just right to get in my pants pocket, catch belt loops. Damnedest things they are, but important. All right. Back to finalizing our comments on writing equations for Bronsted-Lowry acid-base reactions. Again, after you know how to tackle this, then you're in position to get into the real heart and soul of acid-base chemistry, which means analyzing acid-base systems, particularly those which are at equilibrium, from a qualitative, that relates to the equation writing business, as well as a quantitative standpoint, the foundation for which was begun to be laid yesterday in discussion class. All right? Question 1810. We looked at parts A, B, and C last time. Part D. Part D says, consider adding water to half-molar aluminum nitrate solution. Well, you know now, I hope, that before you can write an equation for any reaction, what do you have to do first? Always. PSI. If you don't know what's in the systems you're dealing with, you have no chance to write equations for reactions correctly. You have no chance to understand chemistry of the system at all if you don't know what's in the system. You're not magicians. Aluminum nitrate solution. How does it inventory? Al3+, high positive charge density metal ion. So when aluminum nitrate dissociates in water, because it's an ionic compound, to put Al3+ and nitrate ion in the water solution, the Al3+ ions don't sit there. Each of them reacts with water molecules to form the well-defined hexahydrated aluminum ion, this thing, which you see in the acid-base table. A species which has an acid strength that's just about the same as acetic acid. Do you recognize that if you go to the laboratory and you pick up aluminum nitrate solution, and you observe the pH for the aluminum nitrate solution, which you're going to do in laboratory when you get to assignment 4. If it's 1 molar, you're going to get a pH of about 3. How could you possibly explain that pH if you write this formula? Because something in there is protonating water to create hydronium ion. This can't protonate water to create hydronium ion. You think these protons, these H+ protons, come from the nucleus of the species in question? A nuclear reaction? Hey, Ma, I sure had fun in chem lab today. I ran an acid-base reaction which blew up Alachua County. No, we don't do that. We use extranuclear H+ in Bronsted-Lowry acid-base reactions. Not protons which are extracted from the nucleus. Nuclear fission. Boom, there goes Alachua County again. So this formula is just not good. It can't possibly be used to explain the generation of hydronium ion when aluminum ion is put in the water solution. But this formula can. And here's the reaction which shows how this formula behaves as a Bronsted acid. So simply put, when you add water to aluminum nitrate solution, what you have to recognize in this special case is that in aluminum nitrate solution, not only do you have hydrated aluminum ion and water and nitrate ion, which participates not in the least in the chemistry of the system, this equilibrium is alive and well. And if all you did was write the inventory, PSI, hydrate aluminum ion, water, and nitrate ion. What's the strongest acid? Hydrate aluminum ion. What's the strongest base? Water. So clearly the reaction that's got to occur when you add water to this system is that between hydrate aluminum ion, the strongest acid, and water, the strongest base. There it is. And after it goes left to right, to a very small percentage for fairly concentrated aluminum nitrate solution or any water solution of hydrate aluminum ion, this equilibrium condition is established. So what we're really asking you for D is what happens to this equilibrium when you add water? Look at this reaction. What does this reaction equation tell you?
If you add more water, you have more reactants, you have a bit more product, so it's going to Low pH.
We'll talk about that part in a moment. Okay? This reaction tells you to make the indicated products, hydrated aluminum ion and water molecules have to clobber each other. Because without collaboration, two species can't react. And do you believe that on a time average basis, a given hydrated aluminum ion is going to react more frequently with water molecule to have this reaction go left to right if you up the ratio of water molecules to hydrated aluminum ion? You think you have a better chance to win a fight if instead of 10 of you jumping on some big strong fighter, 100 of you jump on the big strong fighter? You think you have a better chance then? You're damn right. That's all that's going on here. The more water molecules you add, the higher the ratio of water molecules to aluminum ion. The better the chance then you have for aluminum ion to react with water and become these products. So simply put, when an equilibrium system in water solution exists, like this one, if you add water, you will always drive the equilibrium, you will always drive the reaction to regenerate equilibrium in a direction that corresponds to water reacting with something. So we add water to this system, the something with which water reacts is this. So adding water causes more of this to react and you go this way. So in the diluted aluminum nitrate solution, let's imagine we had 50 milliliters of aluminum nitrate, half molar in a beaker. We had enough water to turn it into 0.25 molar. We diluted it by a factor of 2. Since in doing this, more aluminum ion, hydrated aluminum ion converted to those products, in this system you now have more hydronium ions and more of penta-aqua hydroxyl aluminum ion. The hell with the name. Formula is good enough. Swimming around in the resulting solution. But a comment was offered from the audience that said, because of making more hydronium ions in this system, the pH will go down. Do you agree with that? Yeah. You sure as hell better not. Do you really think you can make a system more acidic by diluting it? You have to lower the acidity by dilution. The pH goes up since this is an acid solution. So you've got to be careful when you think about that. But your comment is well appreciated because it drives us to this important consideration. When you add water, two opposing things are happening. On killing the equilibrium by adding the water, as we noticed, you convert more reactant species, which in this case is hydrated aluminum ion, to products. That tends to raise the molarity of products. But don't forget dilution. Because numerically speaking, the dilution factor outweighs the greater ionization extent factor. We increased the degree of ionization, but we reduced their concentrations of all species in the system, reduced the concentration of all species in the system, because all the species in the system now are swimming in a much bigger lake. The numerical explanation of this is in chapter 17. Have you seen it? Take a look if you haven't seen it. Now then, System E, same idea, except that in System E we're imagining we have an acetic acid solution. Say half molar, who cares? And all we're going to do with this system is evaporate. Now when you evaporate, when you add heat to a solution, what material will always be removed preferentially from the system, from the solution system? Water. Don't say that. When I add heat and provoke evaporation,
one with the least intermolecular forces?
The most volatile component of the system, right? That's what you're going to remove from the system. Now for this system, water is the most volatile component. That's why we stated in the notes for E that we're going to remove water by evaporation. At least I think that's what it says. So, if we're removing water by evaporation, then what reaction is going to occur? Because at the instant at which we start to evaporate, the equilibrium is killed. So we're going to go this way or this way to get us back to equilibrium. Now this one's going right to left, right? Because we're taking away water. So we reduce the ratio of water molecules to acetic acid. The only way that equilibrium can be restored is for this reaction to go. Now watch out for the fun question. We evaporated water from acetic acid solution. What does that do to pH? What does it do to pH? Does hydronium ion concentration as a consequence of this evaporation become greater or smaller? Greater. Aha, because that evaporation factor means more than the reaction factor. So, the hydronium ions which are still in the pot, which were not consumed, will now be swimming about in a much smaller lake. Their molarity has increased, and the pH for the system has gone down. This is the opposite of D regarding pH change. Now we go to F. Potassium hydroxide solution put together with sodium bicarb solution. You know how to play the game. I've written the PSIs for us to get going with this. From the PSIs, we start by selecting what? Strongest acid. No, you can pick the strongest base first. That doesn't make any difference. Tell me the strongest acid in this collection of species. As a consequence of yesterday's discussion class, assuming you were there, I hope that assumption is correct. I've told you, discussion class is just as important as what we do here in lecture class. It's an integral part of our proceedings. Look at the information sheet. Something you should have recognized as a consequence of yesterday's discussion class gathering. You see the formula for hydrogen carbonate ion in the acid-base table? You see this formula appearing how many times? Twice. In the acid column as well as the base column. A very interesting species, hydrogen carbonate ion. There are a number of other species which share this property. The property to which I refer is that hydrogen carbonate ion is a stronger Bronsted acid than water, and it's a stronger Bronsted base than water. How about that? So if I'm dealing with sodium hydrogen carbonate solution all by itself, you got any sodium hydrogen carbonate at home? Box this size or a bigger box, white circle on it, hammer, muscle. You got some of that? Commonly called baking soda. Used for cooking, cleaning, good toothpaste. A little abrasive, but it's good toothpaste. They even the manufacturers even recommend if you have bad smells in the refrigerator, buy a box of sodium bicarb, Arm & Hammer, of course. Take off the top, open the box, put it in the refrigerator. It'll help remove the odors. But I got a better idea. If you've got something stinking in the refrigerator, I suggest strongly that rather to try to remove the odors, you remove what's causing the odor. Because I don't think you want to eat that stuff that's making the odor. So, from this list, we recognize this PSI list. Here's our strongest acid. And our strongest base is clearly and as with any acid-base reaction, the acid loses H plus to the base. The base in so doing converts to the product acid of this reaction, as the reacting acid converts to its conjugate base, which is carbonate ion. Extent? Large or small? Large. Because this acid is stronger than this acid. That's all you need to do. The reacting acid is stronger than the product acid. So in general, we expect the extent of such a transformation to be large, because you're going from more reactive to less reactive. This base stronger than this base. It's always that way. Extent large. Now then, let's go to G. Once again, one of the systems to be inventoried is a bicarbonate ion containing system, hydrogen carbonate ion. I think it might say potassium hydrogen carbonate ion, I don't care. Let's imagine that in G we have again sodium ion, hydrogen carbonate ion, and water. But in this case, the hydrogen carbonate ion containing solution is being combined with a solution of Sanaflush. I told you about Sanaflush before, didn't I? Sodium ion, hydrogen sulfate ion, and water. Hydrogen sulfate ion is the active ingredient in Sanaflush because it's a good basic deposit scouring agent. In Florida, we develop a lot of basic deposits. Groundwater, Florida, is considerably basic. You know what the pH is of tap water? Water you drink at home? The water I have right now a sample of in my wonderful periodic table labeled cup. I'll have some in your behalf. What gee whiz is the pH of this stuff I just consumed? pH of Gainesville tap water. You know what it is roughly? Higher. About 9.5. Gee, that's dangerous, isn't it? I've been drinking it since '67 and I'm still here. So I wouldn't worry about it too much. Because pH 9.5, although it's a good deal larger than 7, is still a system which is mildly basic. Hydroxide ion molarity in that is still pretty damn small. But don't go guzzling up any 10th molar sodium hydroxide. So, as always, we look at what we have written, the PSIs, and select the strongest acid, which in this mixture is what species?
Hydrogen sulfate ion.
Hydrogen sulfate ion. The acid-base table tells you that hydrogen sulfate ion and hydrogen carbonate ion, which we talked about a moment ago, are both weak acids whose ability to donate H+ is measurable in water solution because they're stronger acids than water. But you also now have learned about the significance of Ka and Kb. Ka, numerical measure of the strength of a Bronsted acid in water solution. Kb, numerical measure of the strength of a Bronsted base in water solution. What reaction equation defines Ka for a weak acid? If I talk to you about Ka for a particular acid, can you immediately write the equilibrium reaction to which Ka for the acid corresponds? What is it? It's the acid reacting with what? With what? With what? Water! Nothing but. You have to know this. Kb reflects the ability of a Bronsted base to react and produce hydroxide ion and the conjugate acid of the Bronsted base. Kb corresponds to the equilibrium established when the Bronsted base reacts with what?
Water.
Water! And nothing else. Don't forget that. That's what Ka means. The acid has had its ability to protonate water measured. The base has had its ability measured to subtract H plus from water. That's it. Ka, Kb for an acid is always, in Kb for the base, always depends on solvent. And our solvent is water. Since we're only talking about aqueous solutions. Strongest base? Now we got bicarbonate getting in the game as a Bronsted base. Well, like all good acids, this gives the reacting acid H plus to this and makes the product acid of the reaction, which is the conjugate acid of the reacting base. Language sounds like double talk, but it's perfectly systematic. While the reacting acid converts to its conjugate base by H plus loss. What do you think about the extent of this reaction? Large or small? Is this acid stronger than the product acid? Is this the reacting acid stronger than this the product acid? A hell of a lot stronger, isn't it? If you look at hydrogen sulfate ion in the base column, you're not understanding what's going on here. See, hydrogen sulfate ion has its formula appearing in both columns, like hydrogen carbonate ion. But, unlike hydrogen carbonate ion, hydrogen sulfate ion is a weaker base than water. So hydrogen sulfate ion doesn't get into the H plus taking game in water. It doesn't behave as a Bronsted base in water, but it sure does behave as a Bronsted acid, like in this system. Extent? Just look at the table. Hydrogen sulfate ion is a lot stronger acid than this stuff. And now you know from a quantitative standpoint. What arithmetic would you do if I ask you the question from a quantitative standpoint? How much stronger is hydrogen sulfate ion as a Bronsted acid compared to quote-unquote H2CO3? What arithmetic would you do to answer that question? How much stronger is hydrogen sulfate ion than H2CO3 as Bronsted acid? You compare the Kas. Take the larger Ka and divide it by the smaller Ka. Take 1.2 times 10 to the minus 2 and divide it by 4.2 times 10 to the minus 7. I told you I see this table in my mind. No big deal. I've only been going over this stuff for 40 years. Term in and term out. And I wouldn't have it any other way. Well, 1.2 times 10 to the minus 2 divided by 4.2 times 10 to the minus 7 gives us quite a large number, doesn't it? What does it give us roughly? 1.2 times 10 to the minus 2 divided by 4.2 times 10 to the minus 7. Let's write 4.2 times 10 to the minus 7 as 0.42 times 10 to the minus 6. What's 1.2 divided by 0.42? Well, let's make it easy. Let's take it 1.2 and divide it by 0.4. What's 1.2 divided by 0.4? 3? I've seen students go into shock over this. If I ask them to divide 12 by 4, they say 3. If I ask them to divide 1.2 by 0.4, they say, my calculator, I gotta have my calculator. Don't you dare do that in my presence. Because I'm going to take that calculator and smash it to shreds. I want you to use this calculator. No, I won't smash it to shreds. I won't take your calculator from you. But I will remind you that if you rely on the calculator as a crutch to do arithmetic like that, you have been mistaught how to do arithmetic in high school. And those people who taught you like that, if they taught you to do stuff like that with a calculator, they ought to be horsewhipped. And I'm the one who will the horsewhip. And if they do it again, I'll hang them. I'm tired of America coming up short in international education standards comparisons. We were number 1 for the longest time. Now we're number 22 or number 23. It's these damn fools who don't know how to teach who are wrecking this, and I mean it. They're the ones. They're the ones. They're the ones who are rooking you people. I mean it. I'm serious about that. Damn dead serious. I don't think, in general, I kind of like President Obama, but I don't think Arnie Duncan knows a damn thing about education, and he's the Secretary of Education. You want to fix problems like this with money? It's impossible. You fix problems like this by finding out who the good teachers are and letting them be in charge and get the damn administration out of the way. Now, the same thing goes here. You hear that, President Mason? If you see this, I mean it. Get the hell out of my way and I'll give you top quality chemistry students every time. Now, you want to have more fun?
Yeah.
Go ahead and get on your computer and take a look at the online first-year chemistry courses that are offered at such low-quality institutions as UCal Berkeley, Stanford, and MIT. Go on. And I'm telling you that if you learn what I ask you to learn, you beat the hell out of them on any general chemistry exam at the end of the first year. I mean it. They don't touch what we're presently doing. This PSI stuff and learning how to write it, they don't touch it. They stay away from aqueous reaction chemistry like the plague. You know why? Because it's tough to deal with. And that's a shame. Because water is the most important liquid in this world because it is the system of life. The support system for life. I don't know what the hell they're doing, but they can waive their functions all they want and monkey around with wave equations in first-year chemistry. That's wrong. That's not what should go on. What should go on is what we have going on. And on we go. Large. Now look at the acid-base table. You see this stuff? You see some information in the acid-base table about this stuff. What do you find in the acid-base table about this stuff? There's a note underneath the table about H2CO3, quote unquote. What does that note mean? Well, it means, for starters, that quote unquote H2CO3 is not true carbonic acid. Simply put, when you make club soda or seltzer water, which you do by putting CO2 through water under high pressure, most of the CO2 hydrates and converts to this stuff. About 99%. I think it's even more than that. It's less than 1% of true carbonic acid present in seltzer water, true carbonic, club soda. You ever take a warm beer or a warm soda pop, shake it up and open it? What happens? Psst. What's this stuff? What's coming out of that? Carbon dioxide. Because you see, this stuff is not very stable. That's one more reason why it's got the quotes on the formula. It readily falls apart into what? H2O and CO2. And under normal laboratory conditions, CO2 is a gas, isn't it? Is CO2 particularly soluble in water? Yes or no? No. Why not? Not polar, is it? So if we recognize that this reaction is large extent, which it is, and this is the acid product which is not stable and readily falls apart into these two things, and we recognize that this gas product CO2 is not very soluble in water, I now have in this beaker some laboratory sodium hydrogen carbonate solution, 0.5 molar, just like you got in the lab. I took it off our laboratory shelves, 2046L lab. I now took from the shelves also some half molar sodium hydrogen sulfate. What's going to happen when I add the sodium hydrogen sulfate to the sodium hydrogen carbonate solution, which I have in this beaker? What's going to happen? You ever see Alka-Seltzer? Ha! Alka-Seltzer! See it? Look at that. There it is. And now we know why this chemistry goes. Now you know what goes on in Alka-Seltzer regarding the gas generation. Okay? Now then, System H. Sodium sulfide solution. We've talked about the inventory of a material like sodium sulfide in water solution previously. Sodium sulfide, like any ionic compound, dissociates when you put it in solution, water solution. So you got Na plus ions and sulfide ions given to the solution by dissociation. The Na plus ions just sit there. If Na plus ions formed a well-defined metal hydrated ion that had acid properties, we'd have to tell you that. Does sulfide ion just sit there? Look at the acid-base table. What do you know about the base strength of sulfide ion? What's the acid-base table tell you?
Very strong.
Strong, isn't it? Stronger than hydroxide ion. So when you introduce sulfide ion in the presence of water, sulfide ion reacts with water to make hydrogen sulfide ion and hydroxide ion. To what extent? 100% practically speaking. So there's our principal species inventory for the sodium sulfide solution. And here's our principal species inventory for the solution with which this is to be combined, ammonium chloride solution. And we've told you, for this system, we'd also like to write two equations. So as usual, here's the complete PSI for the systems. What's our best acid, strongest acid? I'm listening. And our strongest base? Reaction extent? So if I take fairly concentrated ammonium chloride solution and mix it up with fairly concentrated sodium sulfide solution, like for this system, and you make this mixture in a beaker in the laboratory, would you wish to put your nose right over this beaker as you run this reaction and go like this? You want to do that? You'll get an alarming experience, have an alarming experience. Because the ammonia gas generated by this system will not completely dissolve in water. Some of it's going to percolate up your nostrils. And ammonia is not exactly a pleasant smelling material. You ever watch fights? Do you know what they give the fighter to whiff on if the fighter is dazed because the other guy hit him too strongly? Smelling salts. You know what smelling salts generate? Ammonia! The fighter goes, oh, now I'm ready to go fight again. Now then, is ammonia a good deal more soluble in water than CO2? Why? Ammonia, like water, is polar, and what else? More importantly, what else? Ammonia is also a... Come on, you did this in 2045. Let's put it to use. What is the most important intermolecular association property shown by water? Hydrogen bonding. What's the most important intermolecular association forces shown by ammonia? Hydrogen bonding. They're both hydrogen bonders. They stick together quite nicely. You can make ammonia solution up to 15 molar. Now then, we said two reactions. Now, in making this mixture, from a quantitative standpoint, which solution, since they're each half molar solutions, if my memory is right, they're each 1 molar solutions. Which solution was used in greater volume? In making this mixture, which solution was used in greater volume? Ammonium chloride solution. Twice the volume of the ammonium chloride solution. So in running this reaction, which component of our original PSI has been removed? Killed, wiped out? This one. So the question then becomes, what else is in this mixture that we've made with which ammonium ion can react? Well, ammonium ion is still the strongest acid, because we didn't wipe out all the ammonium ion. So, After hydroxide ion got removed from our inventory, we're looking for the next strongest base, and that is, what is it? Is it this? Yeah. A product, one of the products is H2S. You know about the toxicity of hydrogen cyanide? Gas chamber gas? This stuff is more toxic. You're going to work with this stuff in the laboratory. Uh-oh. But you'll handle it quite safely. What's the extent of this reaction? Small. So this reaction will not effectively produce H2S and ammonia as products. One remaining question, which all follow from our acid-base chemistry. Textbooks today, chemical manufacturers today, still have the unfortunate habit of writing bogus formulas. Now, with any cation and any anion, I can write a formula for a possible ionic compound, like ammonium sulfide. Ammonium ions are imagined to get together with sulfide ions, so I write this formula. So this is a real formula. But does this real formula represent a real compound? Can I make this stuff? Yes or no? Why not? Ammonium ions will react with sulfide ions to what extent? How large? 100%. If sulfide ion can react with water 100% practically, ammonium ion is a better H plus giver than water. You can bet ammonium ion is going to react with sulfide ion 100%. So you've got to watch out for formulas like this, because the compound represented by this formula cannot be made, and it's not going to exist just because I wrote its formula on the board. Pick it up from this point next time.